Hello everyone, and welcome to today's chem lesson. Today we're going to talk a little bit about ionization energy and how we can use the things we talked about in our last video, right? The position of elements on the periodic table, the number of valence electrons they have, the number of shells they have, in order to determine which elements have high ionization energy, low ionization energy, where does it increase, where does it decrease. But before we get into the how and the why and the way it works, we should define ionization energy. Now, if we have an element and we want to know the ionization energy of this element, that number is a amount of energy that is needed to remove one of the valence electrons. So to make this go from 282 to 281, removing one of those valence electrons using some amount of energy. For some elements, right, especially the ones who have low numbers of valence electrons, they want to lose their valence electrons. They want to go down to 0. And so losing a valence electron is not something that will be difficult for them. But on the other hand, we could have elements that have high numbers of valence electrons. And these elements do not want to lose electrons. They would rather gain. And so if you try to take an electron away from something that really wants to gain electrons, you're going to have a hard time doing that. And so the number of valence electrons is going to play a big role in determining if these elements have high or low ionization energies. In addition to the number of valence electrons, we're also going to take a look at the number of shells that each element has. If we compare an element with 2 shells that has 4 valence electrons and an element that has 6 shells that has 2 valence electrons, 4 valence electrons is the number I just used before. They have the same number of valence electrons here, so they equally want to gain or they equally want to lose. The thing that's going to make the difference between these two elements, right, which one is it easier to take the electron away from? It's easier to take the electron away that's further from the nucleus. The more shells that the atom has, the further away the electron is from the nucleus. And the further away it is, the less of a hold the nucleus has, making it a little bit easier to take it away, whether or not the atom prefers that. What we're going to do for this and for all the other trends that we look at is we're going to look at the 4 corners of the periodic table. We're going to look at lithium, fluorine, francium, and unseptium. These represent the upper left, upper right, bottom left, and bottom right corners of the periodic table. Lithium and fluorine are in the same row. Francium and unseptium are in the same row. Lithium and francium are in the same column. And fluorine and unseptium are in the same column. Lithium has 2 shells and 1 valence electron. Fluorine, because it's in the same row, has 2 shells, but 7 valence electrons. Francium and unseptium both have 7 shells because they're in the 7th row together, but francium has 1 valence electron and unseptium has 7. Now when we look at ionization energy, when we talk about ionization energy, we're looking at which one of these elements is it easy to take away an electron from, and which ones of these elements is it difficult to take an electron away from. And first, if we're talking about losing electrons, two of these elements are very obviously ones that would want to lose electrons. Which two are the ones that want to lose? The two elements here that want to lose electrons are lithium and francium. They both have one valence electron. They would rather go down to 0 than go up to 8. Right? It's either gain 7 or lose 1. So these two are going to have low ionization energy. It is not going to take a lot of energy in order to remove these two elements' valence electrons. On the other hand, fluorine and ununceptium over here have 7 valence electrons. They want to gain. It is going to be difficult to make them lose electrons. It is going to be difficult to take away the electrons from these two elements, and so they have high ionization energy. They want to keep their electrons, and on top of that, they want to gain more, right? They want to gain more electrons. And so as we look from left to right on the periodic table, we are going to notice that ionization energy increases as we go from left to right. The more right you are, right, the more to the right an element is, the higher its ionization energy will be. And the reasoning here is based on the number of valence electrons. More valence electrons means harder to remove electrons. But that's not the only thing that we see here. On top of looking across the row from left to right, we can also look at the column vertically. Now we know that both lithium and francium have low ionization energies, but one of them is going to be lower than the other. One of these elements holds onto its electrons more strongly than the other. Which one of these two, lithium or francium, holds onto their electrons more strongly? And why? When we're looking at these two, lithium and francium, lithium holds on more strongly and is perfect in the chat, right? Because it has less shells. This electron is closer to the nucleus than this electron is. It's easier for lithium to hold on to something that's closer to it. It's easier to hold on. I didn't mean to erase that shell. It's easier to hold on to the electrons when they are closer to the atom. And now, that doesn't mean that lithium wants to keep its electrons. It still wants to lose, but it is able to hold on more strongly than francium is. And that means it will have a slightly higher ionization energy than francium will. And as we look up and down a column, ionization energy increases as you go up. And this time, it's due to the number of shells. Fewer shells means a stronger hold on your electrons, making it harder to take them away. So if I were to give you 4 ionization energy values, if I were to tell you that these 4 values corresponded to these 4 elements, could you appropriately assign the ionization energies? Can you take those 4 numbers and put them where they are supposed to go? The 2 lowest values, the 10 and the 20, are going to go to the 2 elements that want to lose electrons. The lower of these 2 is going to be francium. And that means the 20 is going to go to lithium. Both of these want to lose electrons. Both of these have low ionization energies. Lithium's able to hold on a little bit stronger because it has fewer shells. But that doesn't mean it's going to have a very high ionization energy. It just means it's going to be higher than francium. On the other side, fluorine and ununceptium are ones that want to keep their electrons. So they're going to have the 2 higher values. And for this same shell logic over here, fluorine is going to get the higher value, while ununceptium gets the lower value. Even though both of them want to keep their electrons, ununceptium has a hard time holding on to 7 valence electrons because of all of these shells. It makes it difficult to hold on to all of them, and so easier to take one of ununceptium's than one of fluorine's. when we zoom out from just looking at the four corners of the periodic table, these trends show us that basically, no matter where I put two elements, I should be able to tell which of them will have the higher ionization energy, because this trend holds through and it follows through for the whole periodic table. Looking at these two elements, not even needing to know what these two elements are, I should be able to say that Y has a greater ionization energy than X, because it is both higher up and further to the right. These are going to have the highest ionization energies, and these are going to have the lowest ionization energies. And if you're ever asked to compare elements, the higher up it is, right? If I'm looking at X and Y, higher up means a higher ionization energy. More to the right means a higher ionization energy. Just finding them and looking at their placement on the periodic table gives you that information. Next time, we're going to look at another trend. We're going to look at electronegativity and do something similar where we compare the four corners and see where this trend goes. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.